my presentation yesterday, you will recall that we try to analyze the terminology we need, with the terminology linked to instrument properties and in general measurement processes. So I try to extract from the VIM, the International Vocabulary of Metrology, all the terms that we really need to specify characteristics and properties of our instrumentation and of our measurement. Today I left just 4 slides yesterday, which are more on writing rules. Because what I see also in international paper and journals, and unfortunately also from some journal editorial boards, are really a number of mistakes in writing. We are all trained since we are young to use correct grammar and to write properly, but this is for the normal language. Very few care is given and attention to how to correctly write numbers, symbols, and so on. So please allow me to just give you few information which are also coded in writing rules from International Union of Pure and Applied Physics and SI brochure. You can also download the System of Unit brochure, where you also have some of the writing rules. So every time we write a number, result of a measurement, unless it is not a pure number, the number of people attending this event, which is a pure number, we normally need to add a unit. The unit is not an abbreviation, it's a symbol. So it has to be written in the same way for every language. So many times we see mistakes, especially in writing the meters, for example. People think it's an abbreviation, it's not a symbol, so they put it MT, like millitons or something like that, which is totally crazy. But the worst mistake I used to read everywhere is on the degree. The rule is that you have to put a blank space between the number and the unit. And there is another rule that tells you that, if possible, they should be on the same line. So if you're writing your number, you put the blank space and the unit automatically goes on the next line, which happens with automatic now with modern writing editors like Word. Please use a way to force the space in between, because the two, they should stay on the same line. For doing this, there is a trick, which is using the Control, Alt, and space, which forces the blank space to be a letter, not just a blank space. And so the complete 15 blank M stays on the same line. Please use this. It's the way to write in your publication, in your reporting, and so on. But give a look at the temperature, where so many times we see 23, the degree symbol, the blank space, and the C. This is not the way to write, because the unit is degree C. If you write degree as an angle, then it's correct to put it together, because it's 23 degrees. It's not a quantity unit. But if you're talking about degrees Celsius, then you have to follow the rule that the unit is that. Again, for a kilogram and so on. So I leave you this for your consideration. I'm almost sure you don't make those mistakes, but unfortunately we read a diversity of such mistakes. You can use both the point or the comma to separate decimals. It depends on your language. We are now all moving to use the point. But what is important is that you never give interpretation to your numbering. Don't make abbreviation. Millimeters, don't write mil, because I say millimeters. This is nothing, mil. And don't be scared of Greek letters. You can use them for decimals by 1,000 and 1,000. You know how it works. These are the symbols. We have seen them. Bear in mind temperature. can be expressed both in degrees Celsius or in Kelvin. Kelvin are not degrees. Celsius are degrees. Kelvin are not. Kelvin are units, are thermodynamic units. And the rest is there. You have SI unit symbols also for the derived units. And here I just collected some of them with the combination of the base units. I just want to recall you that with just the 7 units we said yesterday, we can measure everything we want just by combining them in a way or another. And then the magic of the decimal system is that we decided to go in 3 by 3, also for quick reading reasons. I like the decimal system. It helps our brain, probably it's due to tradition. Who knows if we adopted a system in base 12, which was not that bad. They were using in the past a system on base 12. We still have base 12 for angles and so on. It has a lot of advantages, which I leave you to understand how many things. For example, eggs are still sold in some countries in a portion of 12, but 12 has many more portions, exact portion than 10. But it makes a little bit of complication in our calculation. So we decided for the decimal. But what is good is that every the mixture of units to get the right ones, they all have a fraction 1. So if you don't go to weird units like UK adopted, not the primary, but traditional system, where you don't have a rationality in between, you always 1. So 1 Pascal is 1 Newton over 1 square meter. And this is great. When you express a number, a value as a number, use the unit symbol. When you express it and you want to say it in words, use the name of that unit in your language. Okay, so don't say 6 centimeters. You have also here some example. You can say some grams, a few kilometers from here, but don't say few km. No way. So that was just a conclusion for yesterday. You will keep the slides for your memory. I don't go very much into this summary, but just to recap, yesterday we discussed after the general introduction of terminology, we discussed words related to instruments properties, which are components of their capabilities to measure in a good way. And we will see today what uncertainty means. That every measurement and instruments, they are somewhere and somehow affected by errors, that you can correct those errors by the calibration, that the calibration has also a second step of use, which is to link the measured value after you calibrate the instrument, use it, let me say in the field, to a given standard. And that finally we said that using the correct terminology is fundamental, not only for correct communication, but also to better understand our system and our procedure. So this is also part of a training me and Carmen we gave to the WMO again, but I try to reorganize it a little bit for the scope of this training. But basically, it's just to show you that this is the same content that we deliver to high-level staff from world networks and national meteorological services. So that was done also for calibration laboratories inside national agencies and so on. Okay, don't go to the content, we can skip this. So first of all, what is the uncertainty? it is this. I like to say it's a logical doubt about our limits to know the truth. And we will say why it's logic. Because it's based on understanding, it's based on evaluating, it's based on logic, but it's a doubt. It tells you, as we said yesterday, you cannot know the truth 100%. We have limits. We have technological limits, mind limits, and physical limits to know exactly the truth. So don't pretend you give a number and that is the truth. Trusting, as we said yesterday, belongs to other areas of society, politics and religion as well. As I said yesterday, only priests ask you to trust without uncertainty. Science is not based on that. So you can say, but I corrected for every error. I did everything. I put my measurement procedure in the perfect and correct way. So the result will be perfect. No, this doubt will still remain. And this is the uncertainty. It's not the error. There is a guide which you can download, which tells you how to express the uncertainty in measurement. And by the way, probably at the workshop of 8-9 June, we will have the honor to listen the chairperson of this JCGM, we said yesterday, Joint Committee on Guidelines in Measurement, in charge to publish this guide. So from this guide, it's written that the uncertainty of the result of a measurement reflects the lack of exact knowledge of the, we can say, true value of the measurement. So it means that the result is only an estimate of the true value. We must say we are estimating measurements. And it arises from our imperfect knowledge. And the way that we correct things is not always completely knowable. So the uncertainty normally represents a dispersion, a range of values that can be logically, but the guy says reasonably, again, reasonably, keep this kind of wording in mind. It's a little bit of philosophy. Logically, reasonably, be associated to the measurement, be attributed to the measurement. So again, as we said yesterday, they are not error bars, these are uncertainty bars. How do we got them? We evaluate. So we estimate the measurement, but we evaluate the uncertainty. Probably we will come back on this because if we say we estimate the uncertainty, there is a way to say we have an uncertainty on the uncertainty, which has no sense. But we will see along our discussion that there are cases where you are not able to fully evaluate the uncertainty, and then we don't have to be too much rigid on this. Nevertheless, what we do is we complete an uncertainty budget. We put all the properties of the instruments and of the measurement procedure, which we are able, hopefully all of them, to understand and numerically evaluate. We put them all together, and with the magic we come out with some number which represents our uncertainty. So the uncertainty is a property. It tells you the range from to where we think the true value reasonably lies, given all the information we have. It means that with my system, I have to document everything. With my system, my calibrated instrument, including its traceability, etc., reasonably, I can tell you that this sample weighs 2.53 kilograms, plus or minus 10 grams, or whatever it is. It is a single value, You cannot have more than one. And you can express it both as a percent or directly in the units, plus or minus 0.1 gram. We have the standard measurement uncertainty, which normally is a standard deviation. Normally, we will see that it's not only normal functions, but we will see later on. We have the relative standard measurement uncertainty, which is the one divided by the absolute value. Okay, so it's 1 over the value that you measured. We have the combined standard, which is obtaining using the standard measurement uncertainty associated with all the input quantities in the model. You may have many of them. And then we will see the expanded uncertainty, which is really the pain for who does measurement, because you are happy that you reduce everything, that you try to reduce your uncertainty to have a better knowledge, a limited range. You want to be more, you want to present something good, but then in the end you have to make it double, at least double, which is not good. But we have to do that in order to represent a wider sample of value, more significant values. Now, I started saying something that is going to be old, because the new revision of the guide is moving in another direction, but this is what we still try to deliver in training courses. There are two types of uncertainties. Maybe you may recall that at university, someone talks about systematic error and instrumental error, random error and instrumental errors. Unfortunately, many professors still use this terminology, which is completely wrong. We prefer to say type A and type B uncertainties. Type A are estimated and then and after evaluated through statistics. Okay, you repeat measurements and you get a statistic, you get a distribution. It can be rectangular, it can be normal distribution, and you get your standard deviation of the same, possibly the same measurement. Because if during your measurement, the measurement changes, well, we are no more making statistic on the same thing. You have to take into account this. Don't put statistical analysis on something that is drifting, for example, or on a sample of snow that is melting in your hand when you weigh it. Type B, the guy says, is everything else. It makes it very easy. So type A is statistics with a distribution. Type B is everything else you have. But this everything else, arises from technical knowledge. You may have calibration, resolution, all the wordings we had yesterday, stability, drift, correct use, exposure, influence quantities in the field, other relationship in between quantities, voltage generator over a home measurement, and so on. All of them are then combined into what we call an uncertainty budget to calculate the standard uncertainty. Beware, this is the subject of tomorrow, that even a non-complete knowledge of the measurement may introduce an uncertainty. Are you sure? How well do we know what we're measuring? I want to measure the weight of this sample. Is the sample in a correct position over the balance? Is the balance well made? Am I really measuring a mass, or am I measuring something different, volume or whatever it is? This is key in temperature, and we will see that tomorrow. I don't want to go very much today on this subject. They are due, the uncertainty on the measurement are due to really a number of problems. For example, how well I'm able to define the measurement. The the column of something in the sky, is it really well defined in terms of the interaction between the instrument, being this LiDAR or radio sounds or antenna or whatever it is? Am I sure? Sometimes we don't have the perfect realization and definition of the measurement. The sampling is not representative of what I want to measure. I'm taking something, I'm thinking I have that, but it is not. And someone else comes to tell me, no, you're not sampling in the correct way. It is not representative. This is also in meteorology, when people hope that data is representative of a large area, but it isn't, because you have a building close to you or something similar. So is the measurement air temperature in that point correct to represent the air temperature in Longyearbyen, or is the air temperature near Eunice at Longyearbyen, where Eunice is warming sometimes, or depending on the sun or whatever? So is this representative? We don't know the effect of environmental conditions. We will see that tomorrow. And this is really another pain on which we are discussing in international committees. You even cannot imagine how much at this point. We don't have exact values of standards or reference material. This happens. For some reference materials, we don't have standards representing enough the measurement. We need to adopt approximation and assumption, for sure. I don't know exactly what I'm measuring, so I try to. But this is the starting of science. You can do that. It's not nothing of these bullet points are negative, and so on. You think you are working in identical condition, instead your snow sample is sublimating a little bit during your, and it's some clean water is leaving, and so the amount of contaminant is relatively changing during your sampling time, just to give an example. And this, of course, we say they play the key role. Unfortunately, they really play the major role in the uncertainty budget. Now, why should we really worry about uncertainty? Why don't we just say, okay, that's the result of my measurement, I hope it's good, and I want to compare it as quickly as possible? Because evaluating uncertainty is much worse than estimating the measurement results. So, first of all, every measurement is subject to some level of uncertainty. We said this, we are not perfect, we are humans. And a measurement result is not complete without the value of the associated uncertainty. You have to put it there, because otherwise, I'm not sure even if your result is on the correct place. Knowing the uncertainty helps you to say if it's okay for your scope. If I have to measure a gold sample for selling, I want to measure it at a milligram. I cannot measure it with an uncertainty of 10 grams. The purpose is to get some money from the old gold I found in my mother of grandmother closet. Understanding measurement uncertainty, of course, is the first step for reducing the uncertainty. If I don't evaluate it, I'm not able. And reducing the uncertainty, it's a good way also to provide to colleagues or your community that you're doing a very good job. Because you show, guys, 2 years ago, we were measuring this at 30% of uncertainty in a relative way. Now, we adopted this solution, this other solution, and we did this, we changed the time of sampling, we did blah, blah, blah. And then we went to 20%. You can have a publication just because you reduce the uncertainty, because you provide to the other a good method, and they say, wow, that's a good method. I never thought to just reducing uncertainty. We just go to the field and take measurements. And in fact, you can distribute this measurement practice, which arise for understanding how you did to reduce the uncertainty and help each other. And then you even go, or communities, they go towards adopted guidelines on this. So why we need to evaluate the uncertainty? It allows us to assess the methods and the results against our what we call target uncertainty, the requirements. I have a target. I want to know this within not more than 10%, but I have to evaluate it. Also, it helps you to say, is this measurement method the best one I can have? If the uncertainty is too big, the answer is, well, no, maybe. Shall we change something? I can go to my director and say, with this method and with this instrument, we will never get our target uncertainty. Please give us a little bit more money to buy a better multimeter. It allows you a correct interpretation and application of the results. I know much more if I have a range in which my results lie, because with this range, I can make a comparison with your range, the equivalency of different results. We can speak more together and get comparability. As I said, it helps you to understand where to make an intervention, where which parameters you have to consider more to reduce your uncertainty. So in general, it helps you to improve a lot. It gives a lot of information. Now, this is a scheme of the uncertainty. You have repeated measurements. I will repeat the scheme in another way. You make the mean, the average. You have the statistical. If it is the same measurement in the same condition with the same instrument in the same short interval of time, we can call it repeatability. Yesterday. Then you correct for the known external condition. You can make a correction, but you will have an uncertainty due to the correction, because also the correction, we cannot perfectly know this. So you have to propagate that. You add it to your statistical uncertainty. So this is type A and type B. And then you have your measurement results. And here we say estimate evaluation of the uncertainty. What you left is unknowable. Leave it as it is. We said what the uncertainty is. Now let's see what it isn't. It is not a mistake. As we said yesterday, don't be afraid to say uncertainty. It's a positive concept. It's not an error. It's not something that works worse. It's not an instrument working bad. Manufacturers, please talk about uncertainties. Don't be afraid. We know what is this. And it is not an absolute fact. Because when we will see that when you make the expanded uncertainty, also, this is why we say we have to evaluate it, but in the end, it is also an estimate that at 95%, 66 and something percent, your measurement results lie within this range, plus or minus your sigma, let me say. And this also means that 5 times you're out of that. So it's not an absolute fact. Again, you have to admit it, even when you're already uncertain. My apologies, I don't know why this telephone is ringing. Okay. So in the end, we say that we cannot know the value due to our limited knowledge of everything. Even in the data analysis, you will introduce some uncertainties. Of course, you will introduce uncertainties which may be statistical or even systematic. If you adopt some sort of processes, every process introduces an uncertainty. Maybe it's negligible, maybe it's nothing, but please keep it in mind. And we said this before. I think yesterday we already got this slide, and which is just an error. It's just a repetition of the fact that error is not uncertainty, but I have to insist on this. For example, if I have a cheaper instrument than someone else, I do not make a mistake over an error. I just have a larger uncertainty. So this is also a way to say that operators, they don't make mistakes just because they have less money than other famous and rich labs. If I have evaluated deviation from a reference value, also from a high quality device by the calibration of the instrument, I do not correct it, then I will introduce errors if I don't do this. The error in metrology is the difference between the indication and the actual value of the measurement. We have to correct errors. If I have an error and I know this number, I have to take it out of my instrument reading. Consider it. Don't leave instruments with error. Maybe you want to leave what we call the raw data. Maybe you want also to leave the raw data as a record. Keep it, no problem. In climatology, it's really a valuable addition if you keep the raw data. But then please adopt the calibration of the instrument and also put your true values together. Why keeping the raw data even if there is an error? Because you don't know, maybe you want to really follow the drift in the ears just as a, because your measurement is another, it's just the relative change of something, and you want to keep track of this by following the drift, not the uncorrected drift. Keep it. It's another measurement which you may want to have in the future, but bear in mind it's from a non-calibrated device and it has an error which you may want to correct. Now let's go on another way to make a scheme of this. Let's start from a true value. This is the agreed or hopefully true value of what I'm going to measure. The weight of a sample, the content, the relative content of pollution particles of a given substance into sample, the depth of an active layer, the temperature at some point, the temperature of the air, the pressure, or some content of the water, whatever you want it to be. I measure those values. And I take the mean of them. The distance in between the true value and what I measure can be as small as you want. This is just an amplification of the scheme, okay? The single measurement value has its own uncertainty and its own error. So every single value I measure has a difference with respect to the supposed agreed value. Bear in mind, measured values are under the same conditions. Okay, I'm not measuring during the drift, I'm not measuring something with different instrumentation. Please, it's the same. Repeatability. So if every single one has this different error, I can make a mean and have a systematic error, which tells me I can measure so many times, but in any case, I will do this error. When I do this under calibration, try to imagine that the line, the gray line average value is the response to the instrument, and the agreed true value is the reference value given by the instrument you use to calibrate your instrument, okay, under test. But in between, you also have a random error, which is the distribution. It's random from one to the other, plus or minus, hopefully, or maybe you have everything on one side, who knows. Then you have your statistical distributed uncertainty, and you can apply the correction. Because now I add all the random information. Maybe I also have some type B uncertainty due to the measurement instrument, the procedure and so on. But when I go after the correction, I still bring myself the uncertainty. It is not just eliminated. It is still there, but now after I corrected for the error through the calibration, my value is, now I can say that, finally, it's accurate. It's an accurate value with an uncertainty of. Less uncertainty, I am closer to a higher level in the traceability. Larger uncertainty, I have less money. I had less time to make the measurement. I was in a hurry, and so on. And this is the traceability. So the guide. Well, we will stop it again in some minutes, so we make a little pause. Allow me just to go through some more slides. The guide gives us also a method to evaluate uncertainty. Please download the guide, it's nice. Give a look at that. You don't have to learn it, but keep it somewhere. So there is an approach, a methodology that has some steps. First, define the scope of your measurements. First of all, I personally, when we start a new project, when we have an experiment, when I have to train people or students, the first thing is sit down together and make a measurement protocol. What do you have? What do I want to take? I have met so many people deploying instruments in the field, and then they don't know what to do with the data. Or they say, yes, we must collect all the data of the temperature of this soil because of what? Why? How will you measure? Is your because coherent with your measurement method? So describe the methodology. Do it before. Make your protocol. Make up your mind. Have a clear scope, write everything. So you are able to identify the sources of uncertainty. If I have it clear in mind, I know now this exposition, I want to measure the heat transferred by radiation into the rocks and understand how much it goes, the heat wave in and out during the seasonal change. Are you sure you're using the correct exposition? Are you coupling your thermometers in the correct way in the rock and so on? You may want to rationalize them one by one, understand the relative weights, quantify them, and then you will calculate based on the knowledge you have. This is not my prescription, it's from the GAM. So 30 years of analysis of experts to provide you with these methods. I think it can be the last slide before we stop a while. So define the measurement process. Normally, you have your measured value, which is in relation with other quantities. For example, please apologize, I always go to temperature, but this can be done for many other quantities. It can be a relation between many other, the input values. It can be the resistance of your system, but also the reference value of your voltage generator in your data logger. Many other aspects like the coupling of your instrument to what you really would like to measure. This is the same for pressure and so on. What you need to do is that, unfortunately, you have to quantify each input quantity contribution. That was the uncertainty budget. And you can do this by repeated measurement. For example, you can make it separately for each of them. One in the lab, one I go to calibration lab, one I test it, and I try to understand and evaluate each of them. One they come from intercomparison, whatever. We will see it later on. And if you find that you have really low contribution, you can put it into your uncertainty budget, but say, well, this is negligible, no problem. Then you have to combine them as a square root of the sum of each of them. If they are like this, you have the Gaussian propagation. It's in the gum. I don't go with big formula here. And then the last step is that you have to expand it. We will see why we have to expand the uncertainty. By saying that normally a measurement result is a function of other quantities you have measured and of which you evaluated the uncertainties. And you evaluate this by repeated, so type A, which is the statistical analysis. We have seen this. Or by estimation of each technical value, which is the type B. We will now go a little bit more into the two differences and different type of uncertainty. Consider again that the new gum is a little bit surpassing this separation, because the more we know of a phenomenon, maybe we are able to move some part of the statistical. Maybe it was noise, it was statistic only, but with a better instrument, we are able to reduce the type A and understand it was a type B, or vice versa. We have more fluctuations, which we suppose it was in the instruments, and it's just statistical something. So they can be partially linked one the other. The type B says it can derive from really a number of aspects, which we will see a little bit later on. But basically, they are instrumental and measurement method. I don't go very much into the type A. It's based on arithmetic and mathematics about what you get from the mean, from the average. So for a normally distributed system, you have this relationship. The random uncertainty is that, but I'm sorry for this a little bit. The point is that you must be sure to adopt this calculation on the statistical uncertainty over the mean, that the mean is of a repeatability condition of the measurement. If something is changing, you cannot adopt it. If you have a drift, if your sample is changing, is losing weight or melting or whatever, don't do that. It's really difficult, for example, in temperature to always have the same value, unless you're not in very stable condition, stable within an uncertainty, and then it's the calibration, and it's it. But when you measure, rarely things are so stable. Okay, this is what you need. I leave all the slides, no time to get, but it's really easy mathematics. We have different types of distribution. Not everything is a normal distribution. Sometimes you don't know. And we have the normal, the rectangular, and the triangular. The normal distribution is the one you know. So hopefully at the end of your analysis, the overall uncertainty is normally distributed, but it comes not from normally distributed terms. Okay. If you add 3 sigma, you go to 99%, 0.7. Normally, we add the value plus 2 sigma in order to have 95% of your representativity. Rectangular distribution is very much used in temperature when you know that you have, for example, a temperature stability is equally given within a range of plus or minus 0.01 degrees is the stability of your liquid bath during the calibration. It's rectangular. We used to keep it as rectangular. There are many other possibilities that went down. Well, you have pros and cons, but that you read that square root of 3 is the way to calculate the uncertainty. And then you have the triangular one. I don't go into this, but I leave it for your records. Now let's go to the type B. I will run a little bit, but type B, we will see tomorrow on with an example, is everything other than statistics. it is based on instrument specification provided by the manufacturer, for example, the calibration certificate, or your experience, how well you know your measurement procedure. This is the definition exactly that talks about previous measurement data, specification, and so on. And let's try to group for our purpose, for the purpose of this training. We have three main groups. The calibration, it is given by the guys who calibrate your instrument. The instrumental components, you need to know them. Stability, the drift, how well you use it in field. There is something that comes from the manufacturer, but something that you may want to evaluate, and something, for example, that comes from intercomparison of instruments, which you know, well, I don't know exactly how it works, but I have an idea. An intercomparison was done, and this is the result, the mean value of this. And from the environmental conditions. That's the key point for our talk. The calibration, I don't go again into this, is the operation that allows you to correct for systematic error by comparing your device with respect to a given reference value with the associated uncertainty. So the calibration we heard yesterday is needed for the traceability. It allows to detect drift or even problems in your instrument. It gives you a correction function, which we call calibration curve, with its uncertainty. And it is required to complete the measurement uncertainty budget. Without the calibration uncertainty, don't even start to set up your uncertainty budget. It's the key, it's the fundamental brick of your building. It ties down the uncertainty, but at those conditions during calibration. We will see this is a fundamental aspect. Normally in lab, the conditions are so controlled that the influence quantities are minimized. The calibration itself introduces the uncertainty associated to the standard that we use and its own traceability. It is a key process of the measurement process. You need it. This is a calibration certificate. And as I said, there is no sense in evaluating uncertainty with an uncalibrated instrument. But the calibration uncertainty is not the measurement uncertainty. I go quickly because we have seen this yesterday. Okay. And how do I put some of the words we heard yesterday here? Resolution, response time, hysteresis, sensitivity, full-scale uncertainty for pressure gauges, for example. You get it from the data sheet. If it is well written, you should be able to get all the information there. I don't go again, but we have these quantities we have seen yesterday: sensitivity, resolution. Put it into your uncertainty budget. Okay. The response time, if you need some dynamic in your measurement, please give a look at the response time. There are normatives how to calculate it. Repeatability gives you some information, but over a short period of time, bear this in mind. Same operator, same equipment, okay? Reproducibility, something has changed. How well my instrument is able to measure again the same thing after some time with the new operator and with the new something. Hysteresis, there are ways to measure the hysteresis. It affects temperature, pressure, and so on. Again, I don't go very much on this. Stability and drift, we have seen all of them yesterday. So this is why I told you today I will go a little bit with a hurry. The drift is something that we need to check, especially in such kind of environment where instruments are not used to be exposed and when environmental forcing may change something. I give you a very easy example of drift. The salt attack to electric contact. The more you stay close to the sea, the more some of your instrumentation may change a little bit. It change what? It change the resistance, it change the conductivity. The data logger thing is reading something as it when it was brand new, but actually the salt is causing something to your electronics and electric contact. This causes a slow drift. This drift is so small that it can be hidden somewhere, but for some reasons, it may be of the same order of the small quantity you want to detect, and you don't know it. Check for that. Do a recalibration. Do a validation or verification sometimes. Environmental condition. They are controlled in laboratory, but they are terrible in field. How can we include the environmental condition in when we define what I measure? I measure this, but under this condition. You have two options. Or you make a part of the definition. For example, I only take the values of pressure when there is no wind, zero wind. I only take the values of temperature when there is at least 3 meters per second of wind, because I know that the radiation is then removed. The effect of the radiation is not the predominant or something. Put it into the part of your measure and definition, and you're happy. Otherwise, you have to prescribe a procedure to evaluate it always in the same way. It's up to you to decide. There is a key new document. In my course, we said that we were talking about a little bit the WMO document, which is the Measurement Quality Classification Scheme. It's a brand new. It was just adopted in 21. I can give you the link to this document. It will be part of the guide number 8, Bible of Meteorological Observation. Who does that? And it talks clearly about sources of uncertainty for surface-based measurement system, which are grouped again into the calibration, the definition, the coupling, the maintenance, and the environmental effects. I don't go into all of them, but please give a look at this, including, for example, the frequency of maintenance is part of your uncertainty. The drift with time, the aging, it's becoming old. The painting is no more very well reflective, the salts, and so on. We have seen this. The expanded uncertainty, please use at least a factor 2. Good use is that you get all the information in what we call K1, the coverage factor. You make all your calculation, and then you transform in the end into a K equal 2, the uncertainty budget. So this is an example of uncertainty budget, which is taken from the document I was referring to, which is a measurement quality classification. Take a look at that. It's nice. It's a way which gives you some scenario, and well, it gives you a way to include some of the quantities we have and to have an overall uncertainty. This is another example. It's taken from the calibration against a reference 1. And you see in the last 2 lines, we got everything. We have to clearly say which is the distribution. You have components in groups, 3 groups of components. The repeatability, the resolution, blah, blah, blah. For example, the resolution is rectangular. Of course, it's within this and that, equally distributed. I don't know. And then you have the double value. For reporting at the field measurement, you have to list all the components, describe them in K1. Be sure 1 is the calibration uncertainty. Don't even start if you don't have it. Identify the environmental effect as well as you can. Tomorrow we will see it's a nightmare. Report the distribution, as we have seen in the table below before. Calculate it with the square root and the derivative. Multiply at the end the coverage factor K to obtain the combined and more representative uncertainty. This is another example where I put the drift. Normally, you don't have the drift during the calibration. It's just the stability under calibration. So, summary, define the measurement, obtain the estimates of the input quantity, evaluate the type A and type B, and apply the model to evaluate your estimate. This is what exactly the guys say. Propagate it, multiply by the K factor, report the results, and try to explain it clearly. It's fundamental that you explain it clearly. Now I go to summary. I'm almost the same last slide. We said it's a property of a measurement result. It must be evaluated for every measurement result, or at least you know that under those conditions the uncertainty is that. So you have your overall uncertainty, which is coherent for more measurement results. I'm doing the same. I bring it in lab. In lab, I have the sample and the uncertainty of the method, and everything is there. There is a general acceptance that it is possible to evaluate the uncertainty of standardized methods and assume it also to future. This is what I said. If you have a clear method, which you use it every time with the same instrumentation, then you can say, okay, the uncertainty of my method is this one. Try to be sure it's appropriate for your target application. The quality requirements within the method are important. Check the quality. Ideally, the method will provide procedure for another user to be able to do the same. The uncertainty, to me, is also a way of preparing a good dinner. A cooker with the same matter can do different tastes, if you like. So you can have different reasons also. But you have to describe it. And please bear in mind, uncertainty must always be reported with just 2 digits. 0.23, 0.00045. But the real meaningful digit must be only 2, because there is no sense to express 1 over 1,000 when I don't know the 4 in front. So if I don't know something in 43, who cares if it is plus or minus 43, some other digits? Please report the uncertainty, but then the number that you bring must be with the same number of digits in the same order of magnitudes. These are the references.
Okay. Well, this presentation is about the calibration of thermometers by comparison. This is one of the activities that the National Metrology Institute do when we talk about the calibration. Just to give you some information, because you are maybe you already hear about this, that the truth is in the past years there was a new definition about the temperature measurement, about the temperature unit, but almost all metrology institutes focus on ITS 19, that it's a very useful recipe to materialize the scale, and almost all the national standards in the world are based on this scale or this recipe. What is the reason of this? That the materialization of this scale, it's let's say easier than the materialization of the unit of the temperature, the Kelvin. It is based in the finite fixed points, the interpolation instruments that are standard platinum resistant thermometers, and interpolation equation. This scale covers since very, very low temperatures. We are talking about minus 273 Celsius degree up to the highest temperature that you can measure by the Planck law. But what is a fixed point? A fixed point is just the change of phase of a substance, and when a substance is changing the phase, this change is not instantly, it takes some time, and during this time the temperature of the substance keeps constant, and we use this constancy of temperature for the calibration of thermometers. At NMI's level, we spend almost all our working life trying to have this type of plateaus as much flat as possible. Okay, in the case, I think these are the fixed points that you are more interested on. The triple point of water is the main is the most important point in all the scale. In this point, we have the three states of the matter: ice, water, and water vapor in a special container. Also, mercury fixed point is very important, but the problem with these fixed points is the mercury is very pollutant. So nowadays there are several projects dealing about looking for new fixed points that substitute these mercury fixed points. And the gallium fixed points is a very nice and easy fixed points because the temperature is around 30 Celsius degrees, very close to the environment temperature, unless in Spain, I don't know, in other place. But I think it is also for your interest. Of course, this scale covers a higher temperature range up to almost 1000 Celsius degree, and also in the negative part to the argon. Okay, but this is for the fixed points usually are using for the calibration of standard thermometers, of platinum resistant thermometers. But we have another type of thermometers. You know that a thermometer is just a device where one of its properties changes with temperature. That's all. We have the liquid glass thermometers or it's just the expansion of a fluid in a capillary stem. The thermocouple is just the generation of electromotive force between two different wires when the strengths of these wires are at different temperature. And maybe you know better the resistant thermometers that can be platinum resistant thermometers and the thermistors. In this case, the quantity or the property that changes with temperature is the electrical resistance. But here we want to talk about the calibration by comparison. In the calibration by comparison, we want to compare the answer of an instrument under calibration to the answer of a standard under the same temperature. We define the correction of this instrument under calibration as the difference between the value of the standard minus the reading of the instrument under calibrations. Please consider that error is the same as correction, but with the minus between them. This is important. It's the same amount, but the error is minus the correction. So we go to our procedure for the calibration of one thermometer. In this case, we are going to use one reference thermometer. So what we need? We need one standard thermometer, and also we need an isothermal enclosure. An isothermal enclosure can be a liquid bath or a climate chamber. In this isothermal enclosure is where we are going to generate the temperature for the calibration of this thermometer. And also we need some devices to read the reading of the thermometer under calibration and our standard. But previously, to start the calibration of our thermometer, we need to check several things. First, the reference standard needs to be calibrated. Second, our isothermal enclosure needs to be characterized. What does it mean? It means that we have to know its stability and its spatial uniformity. Okay, just to keep our experiment under control, just to be sure that the thermometer under calibration is at the same temperature as the standard. And also, and due to the working principle of the thermometers, we need to determine the appropriate immersion depth of the sensor in the isothermal enclosure. Here we have our thermometer under calibration and our standard with isothermal enclosure. The reading cycle would be: first, we measure we read the thermometer standard, then the thermometer under calibration, then we measure again the thermometer under calibration, and as last point, we perform a second reading of our standard. Why we do this? Just to check that the stability of the isothermal enclosure is good enough to perform this calibration with low uncertainty, just to check that our measurement is under control. Once we perform this reading circle, we determine the correction of the thermometer under calibration. That is the difference between the reading of the standard and the readings of the thermometer and the calibration. But Andrea previously says is that it's important to have the experiment under control if we want to have low uncertainties. Okay, so as we are in a lab and we can keep a more control over our experiment, we are going to use two reference thermometers. Okay, this is, I know this is expensive, but this is more expensive than only use one reference thermometers, but it also allows us to control the quality of our measurements. Why is important to use two thermometers? Well, the first point is that with two thermometers, we will check the uniformity of the isothermal enclosure at its calibration point. I mean, we will check not only that the stability inside the isothermal enclosure is stable enough, but the difference between the 2 points where the thermometer is and the standard is, this difference of temperature is also short enough for our uncertainties. But there is also problems. Usually there are problems with the reference standards. And these reference thermometers usually drift. If you only use one thermometer, you don't realize that these reference thermometers drifts with time. I mean, when you use reference thermometers of high quality, they have to be very careful with them because little shock can produce a jump in its relation in its previous calibration, and then this increases your uncertainty. But as soon as you realize of this drift, the better. Also, the isothermal enclosure drifts. And with two thermometers, you can check this drift. This drift is not very usual, but if you use a lot the isothermal enclosures, at the end they will drift, and you need to have this under control. And another point is when you work with baths and isothermal enclosure, the quality of the liquids changes with use and with number of uses and with time. For example, for negative temperatures, we use alcohol for the calibration of thermometers at negative temperatures. What happened? When we reduce the temperature of this alcohol, the humidity of the environment condenses inside the alcohol. After a number of uses, the alcohol has a lot of water, and when the temperature is very low, this water freezes. As it is, these drops of water inside the alcohol freeze, the movement of the alcohol is not so flexible as when there is no water inside the alcohol. And this lack of movement means a lack of thermal homogeneity of the isothermal enclosure. When we check this, it's time to change the liquid inside the isothermal enclosure. So with two thermometers, with two reference thermometers, and with our thermometer under calibration, this is the Reydon cycle. First reading of our first standard, first reading of the thermometer under calibration, first reading of the second standard, second reading of our thermometer under calibration, a second standard of the second measurements of our first standard. With these measurements, we can check the stability of the isothermal enclosure, I mean the evolution of the temperature with time of this liquid, and also the uniformity. Once these values are lower than the values got in the previous characterization of our isothermal enclosure, we are in the appropriate time to perform the measurements and to determine the correction of the thermometer under calibration. Okay, so this is the beginning. Why? Because I told you that the standards have been previously calibrated, so they have corrections that they got in the previous calibration certificates. Check the calibration certificate to include the corrections of our standards. In addition, as Andrea told you previously, the standards or all the instruments drift. Okay, we need to check the history of our standards, and then we need to include this drift in our mathematical model. But also we know that we don't have a perfect isothermal enclosure. It means it has a lack of stability and a lack of uniformity that needs to be taken into account when we calculate the correction. And finally, the thermometer under calibration is its own characteristic, its intrinsic characteristic depending on the type of thermometer we are calibrating, that needs to be included in the mathematical model. Here we have our complete mathematical model. Now, applying the GAM and using the law of propagation of uncertainties, here you have the uncertainty calculation related to the correction. Well, it seems it's quite big, but then we are going to analyze in order to reduce its component. Okay, if we go to the uncertainties related to the readings of the thermometers standards are the thermometer under calibration. Here we have, simplifying, we have a component uncertainty due to the reading of these thermometers, and also a type A uncertainty that Andrea already told you that it's related with the standard deviation of the mean values, okay? We can't establish that the uncertainty related to each of these measurements it's related with the reading and the standard deviation. But usually we use the same system for reading the thermometers. So sometimes, usually, the uncertainty due to the reading of the standard thermometers are the same, and usually the uncertainty due to the reading of the thermometer and the calibration, the two readings of the thermometer and the calibration are the same. So we have to consider this, and also that usually we use two standards of the same model, and probably they have the same correction and the same drift. Assuming this, I mean, or maybe the difference of these corrections and the difference of these drifts are very slow, so we can assume that are the same. We have to check this from the calibration certificate and from the history of both standards, okay? So assuming these two assumptions, we can simplify the calculation of the uncertainty of the correction like this. Now, we are going to analyze each of them. The uncertainty due to the read is a rectangular distribution, and the way of calculation is like this, simplifying. Okay, why is a rectangular distribution? That we don't have knowledge about what is happening inside this limit. If we have a thermometer of 10 milK of resolution, we don't know what is happening at a temperature difference lower than the 10 milK. Calibration of the standards. We go to the calibration certificates that usually give us the calibration uncertainty in normal distribution and for a coverage factor of 2. Drift of the standards. We go to the history of the thermometer, and usually this drift is the uncertainty component due to this drift is evaluated in this way, as a maximum variation, rectangular distribution, but we will consider as an interval the maximum variation, okay? Stability of the isothermal enclosure. We can take these uncertainty components from the previous characterization as the maximum value of the standard of the stability with rectangular distribution, and the same for the uniformity of the thermal enclosure. I want to tell you that we usually tend to be a bit conservative regarding the uncertainty evaluation, since when you are aware about your lack of knowledge about the control of your experiment, you usually tend to be quite conservative, and in somehow increases the uncertainty to be sure that the value you provide with the uncertainty is good enough. But I told you that each thermometer has its own intrinsic properties. If we talk about resistant thermometers, we have to be aware about the hysteresis and repeatability of these thermometers, and also about the self-heating. If we work with thermocouples, we have to know that the wires of these thermocouples are not homogeneous. So we need to check the inhomogeneity. And we work with liquid in glass thermometers. Also, we have to know that they have hysteresis or depression of zero. What is hysteresis? It is a very easy concept that when a material takes time to recover the initial state. That's the basic concept of hysteresis. It means that when a thermometer is exposed at very high temperature, and then at very low temperature, the reading at very low temperature is influenced by the previous history of the thermometer. The self-heating. We are talking about the resistant thermometers and resistant measurements it's impossible to perform resistance measurements without passing the current from the resistance, okay? When a current passes from a resistance, some heat is released due to the Joule effect, and this changes the temperature. This needs to be evaluated. The thermocouple homogeneity of is the wires in a thermocouple are not homogeneous, and the electrons running inside these wires, they don't run so freely as we think in theory, and this has influence in the relation between the final difference of voltage and the temperature relationships. And the hysteresis or the pressure of zero in liquid in glass thermometers is the same as the resistance thermometers. It means that the liquid don't recover in the same way as the glass when the change of temperature between very high temperature and very low temperature is fast. It's fast, okay? Andrea told you that it's recommended to provide the calculation of uncertainty in a form of table. And I agree with this, because in this way you have a very schematic way of expressing all the uncertainties and their evaluation. And here you have an example about the uncertainty calculation of the calibration we have just performed in this presentation. Here you have some basic information about the calibration of thermometers. And that's all. I think perfect of time.